didn't even know this. Let me guess. You came for some calm architecture. I was just reading up on fully associative mapping. See, the funny thing about fully associative mapping is it's a lot like direct mapping. Fully associative mapping, the addressing format, pretty much the same. Only difference between fully associative mapping and direct mapping is that there's no tag, there's no thrashing, so there's no troubles. Now, if you remember our last video, we discussed what thrashing was, and we told you that the tag was needed to identify which line in cache we wanted. If you remember in our last video, we had the illustration of how main memory and cache correlate. So the only difference is for fully associative mapping, the block of main memory can map to any line of cache. There's no tag involved. So basically, each individual line of cache can pretty much hold a block in main memory. But that's going to cause the search speed to decrease, because if the search speed has to go through each line to check and see if it matches to what we're looking for, it's going to take a lot longer than in direct mapping, where we know the tag and we instantly can find the line we're looking for. Crap, got my marker.
I am the one, the way your son don't need a gun to get respect up on the street.
So, for fully associative mapping, we know that it's just dividing into S and W for our address, where W is a location on a line of cache and S is the block in main memory. So, when it comes to mathematics, it's simple. We let W be the number of bits to uniquely identify a location on a line of cache. So we get 2 to the W is equal to our line size. So let's say our line size for this example is 4. 4 is the same as 2 squared, so W equals 2. 2 to the power 2. Nothing too complex. And let S plus W be the number of bits required to uniquely identify each main memory address. So we get 2 to the power S plus W will be our memory size. If our memory size was, say, 16 megabytes, we get 2 to the power 4 times 2 to the 20, which is 2 to the 24. 2 to the 4 is 16, 2 to the 20 is mega. So 2 to the 24. That means 24 is our S plus W. Therefore, S is equal to S plus W minus W. We were told S plus W to be 24, and we were told W to be 2. So 24 minus 22 is S. Daria, hit them with the same example.
Once again, we have another question in which cache memory holds 32 kilobytes of data, and each line of cache stores 32 bytes with a word size of 64 bits each. The main memory size is 1 gigabyte of data. Keep in mind that this is assuming byte level addressing. You may do the following question, or if you don't wish to answer this question, you can skip ahead in the video where we show the answer. As you can see, we start off this question by converting our 64-bit word into bytes. This is very important as we're working in byte level addressing. From there, it can be clearly seen that we use the methods as shown in the video before. Now there you can see a diagram of the partitioning format for fully associative mapping. This marks the end of our video. I hope you enjoyed and thank you for watching.